All right, good morning, everyone. Two announcements. First announcement, we looked over some of the quizzes really quickly. We haven't graded them yet. There were a decent number of people who just took whatever the final answer or the final answer was given in the solutions, the answer key that's posted on Monday, and just wrote that down with no work. Okay. You're not going to get any points. Okay, so this is not an exercise in how well you can copy things that are provided to you. So we're expecting you to see work. I hope I made that clear when we originally described the quizzes, but you're expected to show where those answers came from, not just copying them down. Okay. Other announcement, there's a question about, I forget what week it is, it's coming up in a few weeks, there's a career fair that interferes with recitation period. This happens every year because students are worried about the quiz situation, so that week we'll just have the quiz in class in the morning, and hopefully that'll eliminate that conflict. Should that work well? Will that work for everyone? Okay. Any other questions about that in the quiz? Okay. All right, so we're going to be switching gears quite a bit now. So first, I guess 5 classes were about review of 3260. Now we're getting into a few modules on electromechanical machines. So motors, solenoids, voice coil motors, things of that nature. So we're going to start to build up kind of some of background in what's important for electromechanical machines. Part of this is going to be basically electricity, magnetism, physics. And this is, for any of you who have a physics minor, this is going to be very underwhelming. For those of you who went through the physics, everyone went through the physics undergrad sequence. This is also going to be pretty underwhelming. We're just trying to provide kind of a refresher and the basic knowledge to understand what's going on with electromechanical machines. Okay. All right. So today what we're going to go through is observation of a solenoid. So we'll talk about what's on the desk in front of me right here. Some basic definitions, and then maybe not, we may get into magnetic circuits. So depends how far we get into magnetic circuits. Homework 2 has a magnetic circuit problem on it. I forgot about the holiday on Monday, so we may or may not remove that question depending how far we get through class today in terms of that question. So, okay, so first off, observations of a solenoid. So what I have on my desk here, so I'll electrocute myself, is a solenoid. Okay, so how many of you have ever seen solenoids, worked with solenoids, used solenoids in design before? Okay, a decent amount of you. Okay, what does a solenoid do? Yes. Depends what direction up is. Yeah. This case would be up. Yeah, so exactly. So we'll make some observations here, and then we'll turn this thing on. But basically, you describe it as an inductor here, or a coil, and that's going to create basically a magnetic field, and that's going to interact with something in the middle of here, and it causes movement. And these are probably, in terms of electromechanical machines, one of the most simple things I can bring in and show you. So we're going to start here. But essentially, it provides linear motion. Purpose of these, and it's really simple linear motion. So usually solenoids are used for on or off, and so you don't really have real precise control over how far you move this linear motion in one direction. You can either turn it all the way on or all the way off. It's usually how solenoids are used. There's some more sophisticated ones that I'm skipping over right there, but in general, it's used for sort of really quick movement, and it's really simple movement. So you don't actually have to really control it in the way we'll do with servo control. You can just send a current through it, it moves in one direction until it hits something physical. You're just going to run into something, and that's really good for latches, anything you want to automatically open up doors, latches, things of that nature. Electromechanical relays, so the relays that are controlling whether or not these lights are on, those are usually solenoid based as well. So anything you want to control very simply. Okay, so some observations here. organized here. Okay, where'd the pen go? This is going to be a real bummer of a class without the little pen thing I have. I just had it. It's like, there it is. Oh, is it there? Okay. Okay, so what does the solenoid do? Really briefly, it's just a electromechanical device to convert electrical work into mechanical work. Okay, so the reason why I think it's important to say this, it was just described that this is, you put a current through it, it moves essentially, right? So in more engineering terms, we're taking electromechanical work or electrical work and converting it into mechanical work. So when we say this, we mean this is in the class of tools that are called transducers, right? So transducers we usually think of as tools that convert energy in one domain to another domain. So electrical to mechanical, mechanical to electrical, chemical to mechanical, anything that transduces energy. Okay, usually has linear motion. Okay, so the one that's going to be shown, that's on my desk right now, this is a linear solenoid. But there are rotary solenoids, just as you note. And then uses, used for closing latches. Closing electrical circuits. Oftentimes when it's closing an electrical circuit, we call it a relay. Okay, so used for some very, very simple functions. Okay, so some observations that we'll talk about here. And I'll pass this around. You can go and assess whether or not you think this observation is correct. But the first observation you'll see is lights are a little dim in here, so hopefully you can see it, but you'll see that it's pretty heavy when you pick it up. And you'll notice that there's a chunk of steel in the middle, and that these steel, it's not just a piece of steel that someone milled out with a CNC, but it's actually in a very special form. So it's a bunch of laminated sheets of steel, okay, not just a chunk of steel. So you may ask yourself, why did the engineers bother to make a bunch of little tiny sheets of steel and laminate them together? Why don't they just make one big sheet of steel? We'll talk about that. But that's the first observation. So heavy chunk of steel. Steel sheets are laminated. Okay. Second observation to see is that it's kind of difficult to see because it is covered up in tape. This thing is junk. Okay. So do not be shy about just like pulling on these wires and trying to find the coil that's underneath here. You can't harm this thing; it has no value. I'll be bringing a bunch of junk in this class, and we'll all tear it apart and look at it. So yeah, don't worry about it. Don't be shy with like ripping on this thing. But this center section that's wrapped in tape underneath there has a coil of wire. Tons of wrapped wire. Okay, so next observation requires me to turn this thing on. So what we have here is this is just a regular power supply. Well, not regular power supply. This is a variable power supply. So it allows me to change the voltage of like the power supply that you connect to your laptop, which has like set 12 volts. I can move the voltage here. So let's see. Too high. Dial it down. Okay. So I'm just going to connect basically to a positive and negative terminal here. So then the little moving piece in here, it may be tough for people in the back to see. This is being pulled down by gravity. So if I just sit, it's at the bottom. Okay? And so what I'm going to do, sorry? You saved my life. Okay. Thanks. Tighten these down really well. Okay. So we're going to turn it on, and then I'm going to dial up the voltage. So here we're essentially, most of you probably can't see what's on the dial here, but it's about 0 volts right now. So nothing happens, nothing happens. Keep on dialing up. I'm up to 0.2 volts. Jeez. Okay, I'm a ways away. Okay. 2 volts, 3 volts, 4 volts, 5, 6, 7, and then all of a sudden something happens, right? So nothing happens, nothing happens, nothing happens. And all of a sudden, this little piece that used to be being held down by gravity is now sucked up into the system. Okay, so we've actuated the system, and that happens somewhere around 8 volts. Okay? All right, and if I turn it off, it has this little residual magnetism in it, so it sticks, and when I hit it, and it falls back down. Right? So if I return back onto that level, it moves. So you can see, if it didn't have this residual magnetism issue, you could see how you could use this to do really simple tasks, right? Move something from one location to the other until it basically runs into a wall, right? So you notice this thing stopped moving when basically this centerpiece has kind of a flange that sticks out, and when the flange hits the other solid object, then it stops moving, right? Yes? Yeah. Usually they're spring-loaded. Yeah, so this one's gravity-driven, and I guess assume that it would have something heavier on it to overcome that residual magnetism issue, but most of them are spring-loaded. That's my next question. Yeah. Okay. So observations first before we get to that question. Okay, so this moves pretty fast. Okay, so this actually kind of just takes off. So I get above a certain threshold, all of a sudden it just goes really quickly. All right, so maybe we might want to describe that. Nothing preventing movement until it slams into a mechanical stop. Okay, so following up on this prompt. All right, it's off right now, and what I'm going to do is I'm going to reverse the polarity on this. So this only allows me to output positive voltages, so I'm just going to flip which wire is going to be positive and negative. Okay. What? Oh, yes, that's a good observation. They're both yellow. That's usually your first indication it doesn't matter. Okay. All right, so following that lead, will it matter if I reverse polarity on this? Who thinks it will? 2 people? Okay, who thinks it will not matter at all? Okay. So the not matters at all are correct here. Right. So if I turn this on, same action. Right. So it goes in the same direction. Right. So we'll talk about why that's the case as well. as we get into that subject, we'll actually show that from a mathematical point of view in terms of how voltage transduces in the system. Okay, but the direction of the current is actually not going to matter with solids. It always draws the iron piece in the middle into the center of this. Right, time. So I'll pass this around so you can take a look at it. So it moves in the same direction regardless of polarity. Maybe I should add some meat to that. Electrical polarity. Okay. So just a note, to follow up on the question, like, couldn't you just reverse the polarity of the electrical field or the electrical signal? So there are bidirectional solenoids, and those have two independent coils. And one basically, if you think of a solenoid, just basically attracts the iron core in the middle, right? So bidirectional solenoids would have two coils, and one would attract in this direction, and the other would attract in this direction. Okay. There are solenoids that can get two-way movement, and even more complicated ones. This is like the most simple solenoid you can find. Okay. All right, so for the next few lectures, we're going to be actually going through some of the basic E&M physics that describe why this thing works, and then we're going to start to extend that to more complicated machines, DC motors, AC motors, etc., induction motors, things of that nature. All right. So just kind of a disclaimer, as I said before, this is not meant to be a full-on course on electricity and magnetism physics. It's going to be the real basics of it. And so starting off with the real basics just to understand machines that we care about in this class. Okay. So real basics, a magnetic field. So a magnetic field is basically just a field of elemental particles with a non-random quantum property of spin. Okay, it's the basic idea from that. And so the way in which we are going to represent magnetic fields in this class is how you've probably seen in other classes as well, is just vectors, which give us the direction and magnitude of a magnetic field. So say, for instance, we have some sort of area, A, and then we have a magnetic field, or sometimes we'll call that a B field in this class because we'll use the variable B. And we are going to say, in this case, we have a bunch of these vectors all going through this area. So I'm just showing this by a dense set of arrows. So I'll call this B1. And then say, for instance, for a point of comparison, I have an area that's equivalent, but I have a less dense set of arrows going through this. That's going to indicate a weaker magnetic field. Okay, so that's how we're going to show kind of relative strengths of this. And so if we want to kind of make a statement of the density of this, we call this magnetic flux density, given by variable D. And in terms of units, this is in Webers per meter squared, or also Teslas is the unit for this. So in this case, if we talk about magnetic flux densities here, because of the way I drew this, we would say that B1 is greater than B2. In this class, we're only going to be looking at scalar fields. Okay, so this magnetic field is actually a vector, and it's a vector that changes in space. A lot of electromagnetism physics is quite complicated. We're looking at very simplified versions of it, and we're going to talk about scalar magnetic fields in general in this class. Okay, so magnetic flux density given by B, magnetic flux is going to be given by phi. So if magnetic flux density is B, if we want to get to magnetic flux, we then multiply by the area which this magnetic flux density is going through, or the magnetic field is going through. Okay? So if you want to kind of tie this together with an analogy to other things you've seen maybe in strength of materials and other classes like that, this would be the same way as we look at mass densities, right? So the mass density is the unit mass, or the amount of mass per unit meters cubed, right? If you want to get to actual mass, then you have to say, what is your volume? Right? So very similar here, if you have a magnetic flux density that's given Webers per meter squared, if you want to get to the Webers, you have to multiply by the area it's going through. Just to note, phi1 is greater than phi2. That's because B1 was greater than B2 in this example. Okay, so this little drawing here just kind of shows what I was talking about. This is the case of areal density, right? So this would be kilograms per meters squared. Oftentimes, if you look at, say, a metal sheet, it'll be described in this manner. So if I want to get to mass, I do density times area. So same basic concept for magnetic flux density and magnetic flux. Yes? Yes. Yeah. So I guess let me clarify that. In a given range, right? So we're not going to have a vector field that's continually changing in space. So the flux may be different in different locations of a system, because if you look at a motor, it has multiple locations in which where flux is flowing through the system, right? But it's always going to be scalar values. So if we want to move something, we're talking about putting a force on something. So a magnetic flux can exert a force on a moving charge. So say, for instance, we have a magnetic field going in this direction. So this is B. And we happen to have a charge of value Q, and then this charge has a velocity in this direction. All right, this is going to exert a force on this charge. So if the angle between the velocity of that charge and the magnetic field is theta, we'll talk about the direction of the force in a second, but the force is equal to Q U sine theta. Oh, sorry, I missed the B in there. That's important. QUB sine theta. Okay. Going back to your physics class, what direction is this force in this example I'm showing right here? Up. Okay. So just a reminder, right-hand rule. There's many. Everyone has their own right-hand rule. I think the easiest way is I always just make the magnetic field direction my fingers, thumb, the direction that the charge is going, and then coming out of my palm is then the force. Right? So in this case, let me kind of orient myself to this board over here. So B field in this direction, velocity in this direction, force out in this direction. Going out of space. force, and then this is mutually perpendicular with both of these. Okay, so equivalently, a magnetic field can exert a magnetic field can be generated by a moving electric charge. Okay, so Faraday's law. So Faraday's law is very important for electromechanical machines. So I'm going to draw a schematic here, and then we'll talk about elements of Faraday's law. So say, for instance, I have a coil. So I'm trying to draw this kind of an isometric view as best possible. So I have a coil of wire here, and then I have a resistor that then completes this circuit here. So I have some sort of resistance in line here. And then I have a B field going through this coil, right? So no voltage being applied to this coil at all. It's just sitting there in space. And in some way, I am now creating a B field that's going through this coil. My first question is, if the B field is not changing, what is the voltage across this resistor? Going back to physics class. 0, right? All right, so you need to have a changing magnetic field to cause a voltage by Faraday's law. If I have the case that d dt of this B field, let me label this B, this loop has area A. This is the case equals 0. Then we have VAB equals 0. So I'll label this as A. I'll use lowercase variables. It's getting confusing. VAB is equal to 0, as we just stated. Okay, if I have the case ddt of BA. Okay, so let's ignore the change in time of A. Let's just say A is constant. Let's do the simplest case of we have a magnetic field. This magnetic field is going up through this coil, and this magnetic field is increasing in strength in time. Okay. So then my question is the current in this direction or this direction? Okay. So I'm hearing some clockwises here. So this is, just so we're clear, this is as we're looking down at this coil, right? Still clockwise with that? Okay, we have counterclockwise, we have clockwise. So the answer is clockwise in this case. So with what's happening via Faraday's law is, I think what you're probably employing is that the rule that you have current, and then this is the magnetic field that's caused by the current, right? If you have a current going through a coil, then you say the magnetic field then wraps around via this other right-hand rule, right? To say that you have, and we'll talk about that in a second. Faraday's law is actually that if you have a B field that's changing in time, you're going to have a resultant then current running through this loop that counteracts that changing B field. Okay. Okay, so the current in this direction is going to be, so the current here is going to be in this direction. Looking down from this hoop, it's going to be clockwise. So we're going to have I greater than 0. If this is the direction of current, that means that then the voltage is dropping across this resistor going from B to A. So that means that V, A, B, is less than 0. Okay, then the last case, if D dt BA is less than 0, then we're going to have the opposite case. So then my current, as I've drawn it right here, is going to be negative. VAB is going to be positive. Sorry, what was the question? No, because there's no resistance across this. We're assuming that there's no resistance across this coil. So the voltage at B is higher than A. Yes. Okay. All right. So are we good that current is going in the clockwise direction? Any questions about that? Okay. So then we have current going in the clockwise direction. And so if we have it in this direction, that means that the voltage going from A to B, and maybe it makes sense for the notes if I just write this VBA is positive. Maybe that'll help. But basically, if I look at the voltage A to B, which is by this subscript, voltage AB, right, that's a negative number because we've had a voltage drop across this resistor. So that's kind of the opposite of what you think of batteries, right? Where you look at, that's the difference between the high side and the low side, and the battery is, I drew it a little bit opposite than the circuit you normally see. I guess what I'm saying. Okay. So then the Faraday's law here is then that E, which is going to be the voltage, is equal to negative. This negative captures this basic idea we have here of dBA dt, or that's equal to negative d phi dt. Okay, so the change in magnetic field causes a voltage. All right, so the reason why this is going to be important, this is the fundamental, I guess, element of physics that slows down all electromechanical machines. Okay. How many of you have heard of back EMF in motors before? A few people have heard of this, okay? So back EMF, we'll talk about this when we talk about generators. Back EMF is the basic principle that drives a generator. So generator, think of, you go to Ohio State tailgates and you see the people with the big screen TVs out in the middle of the field, and you say, how are they powering a big screen TV out in the middle of the field? It's because they purchased this little Honda generator that will create electricity from, basically that's a transducer going from chemical energy into electrical energy, and they use a generator based off of this principle to do that. We'll talk about that later. Also, other generators, the alternator in your car, that's a generator. That's how you continually keep your battery charged, or else your battery would only last maybe an hour or so. Right, so that's another example of where this is used. But it also slows down machines as well. So important. Yep, and regenerative braking, yep. Okay, important because this principle is underlying generators. Okay, so as was mentioned by Thomas up front, this would be regenerative braking, windmills, all these things use this principle, underlies generators, and also slows down electromechanical machines. Okay, so say for instance you have a motor and I put a voltage across the motor, it's going to then, with say even the no load condition, it's going to eventually slow down at some value. It's actually not primarily driven by friction, and the bearings in the motor is actually primarily driven by this EMF. This voltage caused by a changing magnetic field. So this is called electromotive force. Okay, so it's not actually a force, it just somewhat acts like a force. Okay. All right, so we just said that E is equal to negative d phi dt, and I'm leaving a gap here on purpose here, is that if we want to have more EMF voltage or more basically force generated by a current running through, these are dual properties, then we can coil a loop n times. And this n times is going to be an n times multiplier on this reaction. Okay. So in terms of the solenoid, which I see is somewhere in the back right now, it's not just one loop of wire wrapped around this ferrous block in the middle. It's a bunch of them. I don't know how many. I'm going to guess a few hundred. But you get a multiplier, so every time you put a new loop of coil, you get then a multiplier in the amount of either magnetic field generated or the amount of electromotive force you're going to get from the system. Okay. Yes?
You said that there were steel plates in the magnetic field that were like wrapped.
Yeah.
I'm kind of, why wouldn't they use wires instead of wouldn't that be more coils then?
Yeah, so if you get, so I agree, and it's a design trade-off. We'll talk about, we're getting to that point. I hope it'll become clear soon, is that, yes, there's the really expensive motors. So think of like motors in a Tesla. They have all these really fancy ways of winding these coils as tightly as possible. And so exactly, yeah, if you want to get a really strong motor, so very high power density out of your motor, you try and wrap as many coils as possible in a small amount of space. Okay. Now that comes with a penalty, because if you want to put a lot of coils in, you have to have really small or really high gauge number wires, which will have higher resistance. So it's this huge engineering design trade-off that we're not going to really get to in this class. All those things, that's, if you want to really learn about that, you actually have to take some electrical engineering courses to talk about those elements. But yeah, really expensive motors have really high density of coils. Yeah, so they even have, and there's some interesting things they do. They even have like square cross-section wires sometimes. And the reason is because the square cross-section wires, you don't have the air gaps in between that you have with round cross-section wires. So it's a really crazy thing that people do. Sorry? Yes, that would be a pain to wind. Yeah, that's so easy. And extrude. It's going to be more expensive to extrude those. So. Okay, so if we want n loops, we get more electromotive force. And then similarly, we can create a magnetic field by putting a current through a coil. I think this is what everyone's pretty familiar with, right? So if I have this schematic here, I have a coil, and my current is going in this direction as a reminder. Kind of the other right-hand rule, if my thumb is the current, then the magnetic field wraps around that current in the direction of my fingers with the right hand. Right? So if I have a coil of these wires, I put a current through it, I'm going to get a B field or magnetic field going through the center by the right-hand rule. The inductance of the system is given by this term right here. where L is a characteristic of the inductor coil. Okay, so again, note that the inductance is scaled by this n, so it's oftentimes advantageous to loop as many coils as possible, right, within reason, right? Also, I forgot to mention too, the more coil you add, the heavier it gets too, right? So that's another thing, right? Okay, so this answers why is there a ton of wrapped wire in the solenoid? It's one wire would not be enough to make this thing move. You're going to need hundreds of these to actually have this happen, right? Because you get a multiplier every time you add a new coil, you get slightly more magnetic flux out of this. Okay, so this is amplification. So why is there tons of wrapped wire in the solenoid? And that's because you get amplification. Amplification. Of the magnetic flux. Okay, so you get a little bit of flux for each coil. So if you just have one, you're not going to have very much. And so what we do is we create machines. Some of them are hollow, some of them are not. But you basically have a coil. I'll draw this out, make these larger actually. So this is looking at if I were to cut this coil in half, and if I'm looking at the cross section. Okay, and so we'll, just like pretty much every other class you've had in physics, we're going to denote current going into the page by X's. And current going out of the page as these dots. Okay, so what direction is the B field here? Up or down? Up, right? This represents current into page. Okay, so if you need help remembering this, just think of this as an arrow. So if you were looking at an arrow flying at you, you would see just the very point of the arrow. And if you were firing an arrow and it's going away from you, you would see then the tail of the arrow, right? So it looks like either a dot or a cross. Magnet wire is made of either copper or aluminum usually. With a very thin layer of insulator. Okay, so who has, with working motors, has ever made a motor smoke before? Who's ever done that? Myself and a few other people in the class? Okay. Yeah. Okay, so what you're doing when you make a motor smoke means you put too much current into it. That means if you look at basically too much power into it, it's going to heat up that coil, and you're burning off that polymer that's separating all your individual wires of your coil. That's what you're doing. And then it's going to lose power because now you're going to have electrical shorts in your motor. So don't recommend doing it, but it's, I don't know, I've done it on accident 2 or 3 times in my life. It happens. So you're not a bad person if you do. So, I had a question in the middle somewhere. Yes. Okay. So the B field is current, right? And then the magnetic field is then the right-hand rule, so that's wrapping around the current. So if I look at this example here, I have current into the page. On the right-hand side, it's going to create a B field that's going up in this direction and down on this side, right? And then here is current out of the page, down on this side, up in the middle. So if I look at the flux in the middle of this coil, through the middle, and I think following that question, it may make sense to actually talk about what's happening outside of this as well. So outside of this, we would have then this wrapping around. Okay, so now getting to the questions of why is there this big chunk of steel in this? Okay, so this has to do with Ampere's law. So this is magnetic field intensity. This is an H in units of amps per meter. In vicinity of a conductor. Okay, so basically, this is just not really a law here. I mean, not a law in terms of the equation, but basically the magnetic field intensity is related to current, and then our magnetic flux density, B, is related to the medium at which this magnetic flux density or this magnetic flux intensity is going through. Okay, so we're going to have the relative permeability. We'll talk about that in a second. We're going to have the permeability of free space, and then H. And H is a function of I. So the larger, the function of I is also, it's a positively correlated function with I too. So the larger I is, the stronger H is going to be. And so we want to get large B fields. This is a fundamental constant, permeability of free space. Okay, so in terms of actual units, this is 4 pi times 10 to the negative 7 henries per meter. And then mu r is relative permeability. Okay, so mu r is equal to 1 in air. And I think that makes sense, right? If mu naught is the permeability of free space, that's free space would be air. Relative would be 1 for air. And then when we have different steels, it's somewhere in the range of 1,000 to 4,000. And so what this means is that the transduction of this magnetic flux intensity into magnetic flux density, or how we can actually direct magnetic flux, or I guess how well magnetic field goes through a certain medium, is about 1,000 to 4,000 times better in steel as opposed to air. So air does not allow the magnetic field to pass very well, but steel directs it very, very well. So that's for steel. If you were to use pure iron, it's around 5,200. Okay, so just kind of as a drawing, you have a coil of wire, or not coil, if I just have a single conductor with current going through it, I'm going to get a magnetic field coming off this. This is given by I over 2 pi r, and this is the direction r. So as I move away from this coil, it's going to get weaker and weaker. What this allows us to do is actually have a really high permeability material such that it does not decay very quickly, right? And so what we can do is that we can use different engineering materials to direct a magnetic flux. Okay, or magnetic field, they're kind of equivalent. All right. Okay, so this is getting to the question of, well, why is there this large steel structure in this? It's basically all motor applications operate in air in a certain sense. So the solenoid is being passed around. There's air in between the two different moving elements. And if you look at the case of a DC motor, there's a lot of air in that. There's not some other medium, right, that has a really high permeability. So you're going to have an area with really low permeability, and then you use ferrous structures to then direct the magnetic field where you want it to go. And you do this because ferrous structures have really high efficiency for directing magnetic fields. Okay, so you have a coil to generate the magnetic field, and then you use steel or some other material with high permeability to then direct the magnetic field to where you want it to go. Okay, so use ferrous structures to confine a magnetic field All right, and so what you're using here is that you have a relative permeability of a ferrous structure compared to the permeability of air. That's on the order of, say, around 1,000 to 4,000. Okay, so you can, with very high efficiency, direct where this magnetic field is going. So we're going to assume, for the most part, in terms of assumptions for this class, magnetic flux is confined to magnetic core. Okay, so what this means in terms of solving problems here, and I think this will be more clear on Wednesday when we get back to class, is that we're going to say we have a coil, and we're going to say, for the purposes of being able to solve some basic problems in this, is that every amount of magnetic field that is generated by a coil is all going to be confined to that magnetic structure, or that ferrous structure. There's going to be nothing lost to air. Obviously, that's not true. Anyone who's been through a physics class understands that that's true, but that's going to be our assumption in this class. And then the last one in the last minute is density of the flux is uniform in this structure. Okay, so that means you have this ferrous structure, this piece of steel, and we're going to say that if we have flux going through it, the flux density in every single region in that cross-section will be the same. It's not actually true, but we're going to use that assumption. All right, so I was not able to get to the example that would help with, I think it's problem 4 on this homework. So problem 4 on this homework will be moved to homework 3. So if you have started on that problem, all your work is not lost. You will get to use that, but I haven't gotten through enough to actually have a homework problem on that. Okay, any questions? All right, have a nice weekend. No class on Monday. See you on Wednesday.